Hello, my name is Sarah Foss, and today I will be presenting the paper A Knowledge-Enhanced Pre-Training Model for Commonsense Story Generation by Jian Guan and others. Commonsense stories are event sequences that are connected by common situations and common actors. To generate a commonsense story, a system needs to be able to make event inferences that are connected to the previous input in a coherent and meaningful way. There are many different methods used for story generation. Some models have generated stories from simple sequences of content, like generating stories from images. Other models have used entity representation to track dependencies between sentences. And yet others have decomposed story generation into steps, then generated an outline of the story from the steps, and then generated the story from that outline. The researchers of this paper used a pre-trained deep learning model along with common sense knowledge systems and inputs with limited context to generate the stories. The reason that the researchers chose this model is that this method of story generation has not yet been thoroughly investigated. Why did the authors choose to use a pre-trained model in their method? Well, the unsupervised pre-training of a model is the process of determining good weights and initialization points for a general model by starting with random weights and initialization points and training the model with an unsupervised learning algorithm. Pre-training promotes regularization, which is the minimization of variance, enabling better generalization in neural nets, leading to better multitasking model generation. Then the model is fine-tuned. So fine-tuning a model is adapting the parameters of a pre-trained model for a supervised learning task. A common way to fine-tune an unsupervised model is to add a new output layer and to train the model with a specific supervised task like classification. The authors of this paper built their story generation with the GPT-2 model, which is based off of a transformer model. A transformer is a neural network that uses an encoder-decoder architecture. In this type of architecture, a sequence, like a sentence, will be fed into a neural network, then have all the output from this network fed into another neural network for decoding. This architecture allows the model to utilize the entire input for the decoding process, which makes it very handy for natural language processing tasks, like translation. A transformer is primarily composed of stacks of encoder and decoder layers. The encoder stack is comprised of n layers, and each layer consists of two sublayers, with a multi-head attention sublayer and a feed-forward sublayer. So, during the processing of the data, first the token sequence is fed into the input embedding layer, which will output a vector representation of the tokens. Next, the positional data will be added to the token vectors so that it will keep track of the ordering of the tokens in a sequence. Then, the vectors will be fed to an encoder layer of the model. So the first sublayer, the multi-head attention sublayer, uses something called self-attention. The self-attention mechanism allows the model to associate each vector in the model to other vectors, or it will allow a model to associate certain words with other words. It assigns scores on how relevant each token in this segment is to the current token. For example, the sentence, "The cat didn't get up from the bed because it was too relaxed." What word is it associated with? Is the word "it" associated with bed, or is the word "it" associated with cat? The self-attention mechanism allows it to score to decide which word is more relevant to it. So to calculate attention, 3 vectors are created from each of the input vectors. Q, a query vector, which is the representation of the current token. K, a key vector, which is a label representation of all of the tokens in a sequence. And V, a value vector, which will be the relevancy score for all of the tokens in a sentence. The attention is calculated by taking the dot product of the query and key vectors of the respective token. Then it is scaled by dividing by the square root of the dimension of the key vector. And then the results are passed to the softmax function, which will normalize the scores. Each output value vector is then multiplied by the softmax score. But one of the really cool things here is that instead of performing a single attention function, the multi-head attention function permits the model to calculate the attention function in H different representation subspaces. Multi-head attention allows the model to consider different weighting to tokens by removing some from consideration during each calculation. The input is then split randomly into H heads, and then the scaled dot product attention function is performed on each head in parallel. The resulting matrices from the multi-head attention function are then concatenated and multiplied by a weight matrix. Then the residual is calculated, and then that result is passed to the layer normalization function. The output of the attention sublayer is then passed to the next sublayer, which is a fully connected feed-forward neural network. The output from that sublayer is then passed through the entire encoder layer stack, so over and over and over again, before it is then passed to the decoder layer stack. The decoder stack is also comprised of n decoder layers. The makeup of the layers is very similar to the encoder layers, except there is a third sublayer which performs multi-layer attention on the output of the encoder stack. The output of the decoder stack will be then passed to the linear layer, which will output a vector of raw logit scores, and then the softmax layer will output a vector of token probabilities, and the token with the highest probability will be outputted. The authors of this paper used a generative pre-training model, or GPT model, which is a model that is based on the transformers decoder architecture. It uses a combination of unsupervised pre-training and supervised fine-tuning for natural language modeling. The unsupervised pre-training of a GPT model uses the transformer decoder stack with n layers. So using different inputs, the model can be fine-tuned for specific supervised tasks, like so the inputs are then converted to token sequences processed by the pre-trained model and then fed along with the labels to the linear and softmax layer. So if we were going to look at classification, so here we'd take our classification inputs, we'd convert them to token sequences, process them by the transformer, and then output them to that linear and softmax layer. GPT-2, which is the actual version of GPT that the authors used, has been shown to capture useful semantic and syntactic features, which make it an excellent candidate for open story generation. So, however, while the model is powerful and stories produced with it have good fluency, they also tend to be repetitive, lack long-range coherence, and have conflicting logic. So as you can see here, if we look at the outputs here, we can see that everything in italics here with the pre-trained GPT-2, that was repetitive. And the context is given here. The first time I saw the results of an accident, and we actually have nothing here talking about the accident in either one of these. So, and there's also there's also some conflicting logic that doesn't make any sense, and so that's underlined there. So what the authors of this paper propose to do is to post-train a GPT-2 model with common sense knowledge. So what is a common sense knowledge? Well, these common sense knowledge systems like ConceptNet or Atomic, they provide additional semantic and inferential knowledge for story generation. So these knowledge bases can help infer and predict related concepts in a sequence, which can help with coherence in a generated story. So ConceptNet is a semantic network designed to understand the contextual meaning of words. So when we see how the data is represented, it's actually represented as a knowledge triple. So we can see the head concept has it has a relation with the tail concept, right? So for example, cross street causes accident, right? So it's that triple there with each concept connected with the cause. Another knowledge base that was used is Atomic. So the Atomic network is an atlas of everyday common sense reasoning containing a mass of textual descriptions of inferential knowledge. So again, the knowledge is then represented as a triple. So with a head concept and a tail concept with a relation R in the middle. For example, with Atomic, we might see person X pays person Y a compliment with the relation X intent to be nice, right? So we've got the two concepts, and again, the relation in the middle. So the aim of this paper was to create a knowledge-enhanced pre-trained model by post-training the GPT-2 model with external common sense knowledge to distinguish reasonable stories from auto-constructed fake stories, to have the model implicitly capture the causal and temporal dependencies between events leading to less repetition, and then to evaluate and compare their model to other story generation models. So their methodology. The authors used a pre-trained GPT-2 model as their base language model. The model that they used 12 decoder layers, 12 attention heads, and a batch size of 10. It was trained on a 40 gigabyte data set called web text that was scraped from 8 million web pages linked from Reddit. So the authors then post-trained the model with triples from ConceptNet and Atomic common sense knowledge-based data sets. The triples were transformed into natural language sentences using a template-based model. So here we can see, so if we saw Eiffel Tower at location Paris, which came from ConceptNet, we might see Eiffel Tower is at Paris. And in Atomic, person X dates for years, OFX continues dating. We might see person X dates for years, person Y will continue dating. So just more, kind of a better fluent sentence there. It's not a triple. The model was trained with the transformed sentences to add semantic and inferential knowledge between entities and events. The model was then fine-tuned, so after the post-training, it was fine-tuned with ROC story corpus. On top of that, the authors also added an auxiliary classification task of determining true stories from fake stories. So in order to do that, what they did is they created 3 additional sets of stories. These were all fake. They created stories with sentences in a shuffled order, so that would be in logical order for the stories. Stories with a randomly replaced sentence, so adding an unrelated topic to the story, and then stories that repeated a sentence, so that would have some repetition. They also added an additional layer to the model to compute a softmax score to predict true stories and fake stories. The authors evaluated their stories using ROC stories, a corpus of over 100,000 5-sentence Commonsense stories. The stories were then tokenized into byte pair encodings with a vocabulary of over 50,000. The names in ConceptNet were removed and replaced with placeholders, and in Atomic, the person X and person Y were replaced with placeholders as well. Finally, they randomly selected stories and knowledge sentences for training, testing, and validation. They evaluated their model against a list of top-of-the-line natural language processing story generation models. And in particular, they focused on GPT-2. So they focused on comparing their improved GPT-2 against kind of original GPT-2. So when it says GPT-2 Scratch, so that is GPT-2 without any pre-training at all. And then they also looked at GPT-2 with some pre-training but without fine-tuning, and then GPT-2 with fine-tuning as well. The metrics they used were some quite common natural language processing metrics like perplexity and blue score. They also looked at coverage and repetition and distinct. Now let's take a look at some results. So here we can see some generated stories. So we can see generated stories from both the baseline models and the author's model. Let's take a look. So the context given was Male was driving around in the snow. For the GPT-2 fine-tuned model, the output was he noticed a snow globe blocking his road. Neutral, he backed up the car and got a snow shovel. Male used the snow, shovel the snow and shovel the snow. Now the snow is gone, but he has snow boots and snow gloves. So it doesn't make a whole heck of a lot of sense. Now let's look at the author's output. Suddenly, his car broke down on the side of the road. Male had to call a tow truck. The tow truck came and took Male home. Male was happy. He was able to get home. So that's really, really lovely. It is a coherent, logical story. So we can see in this instant that there has been definite improvement. Let's now take a look at the metric evaluations. In this table, all of the bolded numbers indicate the best results here. As you can see, the knowledge-enhanced GPT-2 model outperformed all of the GPT-2 baseline models here in terms of perplexity, and it had better blue scores than all of the baseline models, which indicates a higher fluency and more overlaps with the original stories. The model also outperforms all of the other baseline models in terms of coverage and in distinct scores, indicating that the model can generate diverse stories with more knowledge. However, all the pre-trained models, so all these GPT-2 models here, including the knowledge-enhanced ones, tended to have higher repetition scores, indicating that the pre-training may result in a higher amount of repetition in stories, although the author's knowledge-enhanced stories did have better repetition scores than any of kind of the baseline GPT-2 models. So in conclusion, the knowledge-enhanced pre-training model for Commonsense story generation outperformed the other top-of-the-line baseline models in almost every category. By combining the effectiveness of a GPT-2 model with the Commonsense knowledge of ConceptNet and Atomic, the authors have created a framework for better open story generation with superior coherence and fluency to current models. Thank you.